Hello and welcome. In this lecture, we're going to be going over climate change science. And that's really just to give you a background on what the general thinking is within the field and why we're so concerned about the changes that we're seeing in terms of global warming. So first off, again, remember that we're talking about this planet. It has a limited surface, it has limited atmosphere, and it has a lot of people on it currently. When we think about population and population growth, it's important to remember that there are a lot more people here than there used to be. We're pushing towards almost 8 billion people on this planet. So, and most of that population growth really happened in the last 100 or so years. So, given that there's more people out there, and given that we've had this incredible change in technology in the way that our expectations for lifestyle, there's been a shift not only in the number of people, but in the wants that those people have. And that has led to a wide range of different types of production that we pursue, from technological to infrastructure, etc. Now, that does result in a lot of waste and a lot of items and a lot of energy that's used to create those items for the public. And very often we don't really realize exactly how big of an impact that is. So we often think about the trash that we produce as what we throw away in our garbage. But if you look at per capita waste, it's about 5 pounds per person per day. But what we don't realize is that there's this whole range of waste that occurs upstream of us actually getting a product. So when we get a product, most of the waste that and energy expenditure and carbon emissions, etc., that happen to produce it happened way upstream of when we actually reach it. So for every 4 pounds of per capita waste that we throw away, industrial waste accounts for almost 300 pounds per day. And there's hazardous waste and medical waste and other types of waste. It's also important to note that we, given our reliance on animals and meat production, the waste that's produced by animals is many times what we produce in terms of what we throw away. So about 130 times what our personal human waste is. So when we think about all this we're producing, all this energy that we're putting into this, we need to remember that we have a limited atmosphere that we're putting energy into or emissions into. And that's most of that atmosphere really is a fairly thin shell. Most of that atmosphere is within about 10 miles of the surface of the Earth. So when we're thinking about all these different things that we do in terms of agriculture, in terms of energy production, in terms of the mining and other things that we do to create the infrastructure that we have, we are putting out a lot of emissions. So when we think about the greenhouse effect, or the way in which the Earth is increasing in temperature, this has been something that we've been thinking about for quite a long time. Some scientists back in the 1800s actually thought that this might be the case. So as I've discussed before, the overall idea here is there's a balance between energy that hits the Earth and energy that gets reflected away. So that some of that energy comes in, some of it reflects off the Earth's surface and goes back into space, but some of it gets trapped by gases in the atmosphere that reflect it back into Earth or absorb that energy and heat that heats up the Earth. So one thing I should just say as I move into talking about what that means, the greenhouse gas effect means for our climate, I should just distinguish between climate and weather. All right. So sometimes these terms are used exchangeably, but they really are generally talking about something different. Climate is really what we'd expect for an average weather across a period of time for a location. So maybe you take 20 years and you average out, and that might be what you'd expect for the climate of that location. Weather is the environmental characteristics at a given point in time. So if you looked out your window, you could say the weather is sunny or it's rainy right now, right? So that would be more what we're talking about when we're talking about weather, sort of more immediate effects that are going on at a specific situation. So when we're talking about climate and overall temperatures, and we're looking at these average temperatures across the globe, well, what we're seeing is overall they're increasing substantially. And here's just a general chart showing this increase in temperature. So that at this point, we're 2020, we're at about a degree above what we used to be if we compare to an earlier reference point. Now, this increase in temperature is accelerating. And what we're seeing is that out of the 6 hottest years on record, 6 of them are in the past 6 years. 2019, last year, was the second hottest year on record, for example, right? So we're seeing this increase in temperature on the whole. Now, we've been thinking about climate and global warming for some time, and there is I'm referring to the IPCC report, which is a report put out by the Intergovernmental Panel on Climate Change. And this 5th report is the most recent report about 2014. It is put together by about 800 different authors. So a lot of people put in energy to thinking about these issues. And what did that report find? Well, I'll just give you the overall summary. So first, they found that there's a human influence on the climate system is clear, and recent anthropogenic emissions of greenhouse gases are the highest in history. Anthropogenic means produced by humans. Recent climate changes have had widespread impacts on human and natural systems. Continued emissions of greenhouse gases will cause further warming and long-lasting changes in all components of the climate system, increasing the likelihood of severe, pervasive, and irreversible impacts for people and ecosystems. So overall, this report found a lot to be quite concerned about and really recommended that we keep our increase in temperature globally to below 2 or 1.5 degrees Celsius. And we'll talk about how actually a follow-up report really recommends us trying to keep it below 1.5 degrees Celsius, which would require fairly dramatic action on our part. So I want to talk here, before we go into some of the IPCC findings, about a few different factors that influence how energy is absorbed into the earth and how the climate is warming. So there's 2 things I want to talk about. First is how much light is reflected. Well, it turns out that that's actually a really important question. What you'll find, unsurprisingly, is that different types of terrain, different colors, will absorb or reflect light differently. And we all are generally familiar with this. Now, the term that we use in climate change science is albedo. And what you'll see is, when the sun hits, say, a wooded area with lots of water, more of that light gets absorbed into that surface. Whereas if it hits something like snow or ice, a very large portion of that light gets reflected back up into the atmosphere and possibly out into space. So when we're thinking about albedo, a black surface or a very dark surface has 0 albedo. It means it's essentially absorbing everything. Where a perfectly reflective surface has a 1 albedo. Now, on average, the Earth has a 0.3 albedo, which means roughly that 30% of the radiation is reflected and 70% of that heat and energy is absorbed by the Earth. Now, there are some gases that are made by humans that actually reflect a fair amount of energy. So some of these are natural gases that go in, and some are made by humans. So aerosols, for example, that can be put off by fires and by volcanoes can actually prevent light from reaching the Earth, and that can actually have overall cooling effects. We also have other types of aerosols that come out of our industrial processes that do this as well. Right? So there are different cooling factors that exist that counteract some of the heating factors that we'll talk about shortly. All right, so when we're thinking about the greenhouse effect, it's that ratio between the reflection of energy and also how much these gases are influencing the balance so that we're absorbing more of that energy into the Earth. Well, there's a factor which we call radiative forcing. And these are the factors that influence this ratio, this balance between absorption and release of energy. All right. As if a factor increases absorption, that increases that energy, it's called positive forcing. All right. If it's something that decreases that absorption, it's called negative forcing. And we'll talk about how different factors have these different relationships to that balance. All right. So we'll talk about different climate gases, climate-related gases. But as you know, one of the the biggest one that we really talk about is carbon dioxide. And just to give you a big picture look at how carbon dioxide tracks with temperature, if you look at this, you have the CO2 concentrations on the top in blue, and below in white is overall temperature. And you see 800,000 years back that the levels of CO2 really closely match temperature over that period of time. And remember, this is a very long period of time. So humans probably evolved somewhere around 500,000 years ago. So this is human history, right? So what we're finding is that CO2 levels are getting really very high, extraordinarily and historically higher than we've ever seen. So 2019, we're seeing concentrations about 415 parts per million. And if we continue for 40 more years, sort of in our current path, our current trajectory, we could expect to see that around 600 parts per million. So really, really high levels of CO2 that we're experiencing right now due to our emissions. Now, when we think about this variation in temperature and what this could mean, when we think about just a degree, we don't normally think of that as being a particularly big thing. If we think about the weather outdoors and 1 degree higher versus 1 degree lower, we might not think of that as being particularly important. But 1 degree across the entire globe can make a huge difference. So, for example, if we look about 17 million years ago, 17,000 years ago, that was our last ice age. And we see that that's, marginally cooler and at a lower point in carbon dioxide emissions. Well, that made a really big difference on the globe. Just that dip, that small dip that we saw there as compared to the big changes that we're seeing currently. So at that time, Seattle, the Washington area, was under almost about a half mile of ice. So if you think about that, that's about 5 space needles for Seattle above you would be covered in ice. So you can think about just looking up. So these small changes in climate over many, many years can have a huge impact on a globe, on global climate. All right. So when we think about this temperature, we might want to say, all right, what is really causing this increase in temperature that we're seeing recently? Well, there's a few different things that you could think about. And a lot of people have thrown out a range of different ideas for why this is happening. And this has often come up in conversations around climate change denial and other explanations that have been used to try and describe this as not being due to carbon dioxide so that we don't have to worry about changing our emissions or our patterns of consumption. So some things that have been proposed are things like orbital changes. This really doesn't seem to have a big impact, and you can see the orbital changes in the blue line, right? So we're seeing that has stayed pretty constant over this period of time. You could think about fluctuations in solar energy that are coming and hitting the Earth, and here again, we're not seeing a big change over that period of time. We could also think about volcanic activity. So volcanic activity typically has a cooling effect because it blocks out sun, right, and reflects more sun. So we do see some changes there, but that's not likely a cause. And if we take all these natural factors together that are not due to human activity, they don't really seem to track at all with temperature. Right, so they don't seem like a good explanation for why temperature is increasing. Now, there are other factors that might be causing this, and this might be changes due to human factors, right? So one example might be that humans have actually dramatically changed the face of the globe. We've turned about half of the globe into human modified space, so agriculture, etc. Right? So we've had a huge impact on the actual surface of the Earth. But that doesn't seem to have had a huge impact in terms of likely impact on increasing temperature, partially because forests actually absorb a bit more of the energy. Now, forests and trees have an interesting impact. They can have cooling effects, especially in urban areas. But overall, if you reduce forests, it actually has a cooling effect. There could also be ozone. Ozone has a minor impact. It tends to be very focused around the surface. So increase in the ozone along the ground can have an increasing impact in certain areas, especially in urban areas. So that might have a small role, but that doesn't seem to be explaining it. And then you might have aerosols, and I've already mentioned that aerosols are among some of those factors that have a negative forcing effect or cooling effect on the atmosphere. So when we think about these different human factors that could be influencing the climate, it really looks like it's these greenhouse gases. So if you add up the greenhouse gases, we see this increase over those periods of time in terms of impact on that temperature. And if you add all those human-based factors together, you see a line that actually really tracks very well with the temperature increases that we're seeing. And if you add all those factors into this complex model, you'll find that the model, based upon what we know about all these different factors, really tracks quite well with temperature. So what is this suggesting? It's suggesting overall that the major driver in terms of forcing is these greenhouse gases. Now, the IPCC report has actually looked at these factors, and they're looking at this observed warming, which is shown in the black bar there. And what they're seeing is that in terms of contribution, it's primarily the greenhouse gases. And there's other anthropogenic forces, such as aerosols, etc., that might have negative impact. But overall, when we look at those combined human-caused forces, you see that produces the orange bar, which really matches quite well with that black bar. So it's suggesting that most of this change that we're seeing in terms of climate is due to human action. All right. So I just told you about this report. The report was put together by a lot of people, but a question is asked, do scientists on the whole, climate scientists, believe that humans are causing climate change? And you've probably seen the 97% statistic thrown out, and that's previous studies that have looked at people working in the area of climate to see how many of them agree about this human cause of climate change. And I will say that has that's already an overwhelming indication of climate scientists agreeing. But a study that was just produced in 2019 found that there was 100% agreement among 11,000 articles published in about the first half of 2019. So we're seeing a very strong scientific consensus that this is the cause of climate change. So why are scientists so confident? Well, there's this correlation that we're seeing. So this historical correlation between CO2 levels and temperature. We have pretty good historical data around temperature. It's a very fascinating thing. We have so many data points that goes over hundreds of years, and we can make estimates from other information that we have, biological information that's carried in our ecosystems and trees and other things like that. So we can make estimates around temperature going back for quite some time. And currently we have very precise estimates. We have hundreds and hundreds of thousands of stations measuring sea, air, and air temperature at all points in time. So a huge amount of data that we're using. We also are really confident that not just because of the correlation, because we know that correlation doesn't always mean causation, but we also know a lot about the actual chemistry of these greenhouse gases. So we have a wide range of different laboratory studies that look at how they interact with light and what is likely to happen in terms of impacts on climate in an actual real world setting. And then we have atmospheric observations. We can actually look and see how the light is reflecting back into the Earth from the greenhouse gases. And we can actually tell how much of that light is being reflected from different types of gases based upon the way that it influences light. So we actually have direct observations of the greenhouse gases in action. And then we have models. So these are the ways in which we actually use computers to make estimates based upon the data that we have around different types of emissions. And we see that these models actually perform incredibly well. Even old models that weren't very complex perform very well. And these models combine a lot of different information to try and give us estimates for not only where we are, but where we're likely to go in the future. So when we think about these greenhouse gases, there's a few things to just know. So the first thing is you should know that the major greenhouse gas actually is water vapor. It accounts for about 36 to 70% of the greenhouse effect. Now, we don't normally talk about water vapor very much because it isn't a forcing effect. We always have water in the atmosphere, and there's sort of a limitation on the water that can be in there because get enough water vapor and it will rain, right? But we'll talk later about how the fact that increasing temperature can allow more water vapor into the air. So, but we don't think that water is actually what we call forcing effect. So it's not one of the greenhouse gases that is actually causing this climate change. The actual causes are primarily carbon dioxide, and you'll see when we look at those causes over time, this is just a chart. Carbon dioxide is in black, and then we have methane in gray, and then we have other factors as well, nitrous oxide, etc., that do make a substantial contribution. But we see that the majority of this effect is due to carbon dioxide. Now, what I'll note is that all greenhouse gases aren't created equal. Some actually have a greater impact in terms of their global warming potential. So for every parts per million of that substance, it can have a stronger impact. So our standard for looking at global warming potential is actually carbon dioxide. So we'll see that the global warming potential of that is 1. But we have other things like methane. Methane has a much stronger global warming potential. So it's about 21 roughly in terms of global warming potential. So per part per million, methane actually has a bigger impact on warming, although there's less of it in the atmosphere than carbon dioxide. You also have nitrous oxide, which has a high global warming potential. And then we have other fluorocarbons of various sorts that can have actually incredibly high impacts in terms of global warming potential. So there are a lot of things that we're putting out into the atmosphere that have potentially have a really big impact that we can think about actually mitigating to decrease that impact. So when we think about emissions and warming, we're going to talk about this later, but when we think towards that future, there's a range of directions that this can go, and a lot of this really depends on how much we reduce our carbon emissions. And we can see different models. These are RCP models, which I'll talk about later, but they look at how much we reduce our emissions and what the likely impact on temperature will be. So if we see at the top, we're looking at annual emissions, the red line being sort of a worst case scenario, and I think there's a blue line at the bottom being sort of a best case scenario. And we see how that will pan out in terms of the future. Now, one thing you'll note here is that the divergence between those lines gets very extreme towards the end of the century. But even up to about 2040 or so, those lines are actually pretty similar. So we don't entirely know exactly how that's going to diverge in the future, and that's based upon our modeling of what that's likely to look like. That being said, if we look at those different possible futures, you can see below that the different colors, so going from gray to the black line, can result in very different potential temperatures. So along the side, you'll see that they range from 0 degrees to up to 5 degrees. So we see that gray, that worst case scenario, being around 5 degrees based upon IPCC estimates. Okay, so the way that this goes in the future will really depend on how much we're able to cut those emissions. All right. So when we think about global warming, a question one would ask would be, what does this actually look like in terms of how it's impacting weather and our climate systems? All right. So I've already talked a little bit about how the fact that this increase in temperature and for the globe has led to a flattening and widening of the range of weather that exists. So we're going to see a wider range of different types of weather that gets much hotter than it used to. So those extreme weather events are going to be much more common. So we'll see slightly less very cold weather, but in some cases we'll see, but it's actually not that much of a reduction, whereas we will see a lot more of this really hot weather in the future. All right. So we're seeing increases in these sort of extreme weather events globally. So here's a picture showing in red extreme temperatures, droughts and fires. We're seeing in blue floods and mudslides, and we're seeing in the yellow storms, right? So we're seeing an increase per year of these extreme events. And the scale on the side goes from 0 up to 800 events per year. Okay, and on the end we have 2018. So what's going on here? How is this extreme weather happening? Well, weather is actually really a process by which energy is redistributed within the global system. So we know that more light hits at the equator. So the equator tends to be hotter, right? And that energy actually gets dissipated throughout the globe through the global conveyor belt, which is water systems that move throughout the globe. You have the jet stream, which moves warm air throughout the globe. So there's ways in which overall energy is moved from the warmer parts of the globe into the colder parts of the globe, all right, to keep that energy cycling. Now that is not sort of equal in terms of the way that it distributes. So a 1 degree change at the equator leads to about 3 times that amount of change at the Arctic, because a lot of that energy is going up and having a really big impact in Arctic areas, which are covered in ice and provide some of that heat sink. Now, what we're finding with this change in temperature is that there's a disruption of these weather patterns. These extremes are occurring. So what we're seeing is that the jet stream is actually getting what we call, essentially, it looks wavier, right? So we see right here that there's curls in that jet stream that are pretty substantial. And what this can mean is more extreme weather in terms of longer duration events that are extreme, temperatures, odd temperatures happening places we didn't normally see them, and just general disruption. Now, some examples of this is looking at how cold weather evolves. So we're seeing real disruptions there. So we have what we call the polar vortexes, that center of cold air that is centered around the poles. And normally you have that low pressure pattern in that area. But what we're starting to see is strange events where the jet stream is bringing warm air into the poles, so that you have a high pressure pattern that actually splits the polar vortex. And this polar vortex goes down into the United States, for example. So we see here in February 2018 where the polar vortex split. And we saw in northern central states, we saw temperatures down to negative 77 degrees Fahrenheit. So really strange weather, unusually cold weather that you wouldn't expect. And at the poles, we saw temperatures that were about 50 degrees above what they would normally be. 50 degrees Fahrenheit above normal. So really strange events. You also see these sort of normal jet stream events. This is just a picture of what it would normally look like using actual weather patterns. But you see here, this is splitting that I just talked about, where we see a picture where the jet stream actually just shot straight through the pole, right? And the Arctic, producing that warm energy. Now, this happened again in 2019, and this has been happening regularly over the last few years that we've had unusual heat waves in the Arctic. Here was a fairly substantial one where the polar vortex actually split into 3 different parts. And we saw again that those cold weather patterns going into the central states in the United States. So we can see sort of general disruption and disruption of weather patterns globally. Now, how does this relate to other types of things that we might be concerned about? Well, we know that there is concern about sea level rise. And this really relates to ice and the way that the poles are influenced by these increases in temperature. Well, what we're seeing globally is this increase in water levels. And that adds up to about 3 millimeters per year on average that we're seeing currently. So how does melting ice influence sea level? So one is that there are 2 different ways that melting ice impacts us. So there's melting ice that's resting on land. And this is the ice that's likely to that will actually increase sea levels, right? So these are glaciers, for example, glaciers in the mountains, and ice sheets. And ice sheets are massive glaciers that cover the Arctic, for example. Now, there is also ice melting that doesn't actually increase sea level, and that's when the ice is already floating on the surface of the ocean, right? So these are things called ice shelves. So this is ice that extends out from ice sheets, but is actually floating on the water. And then there's sea ice, generally, that floats around in the oceans. Now, those ices don't influence the water level because their pressure, the water is already influenced by that floating in the water. So when it comes to the land-based ice, we can think about glaciers in the mountains. So we're seeing big influences on that based upon climate change. So we see from 1955 to 2004, this is just a picture of a glacier in the North Cascades, and we're seeing that around the globe, that these glaciers are receding. We're also seeing that sea ice in the Arctic is substantially decreasing. We see the blue lines compared to the dotted black line, which is the norm, right? So we're seeing increasing sea ice melt. Now, I'll note here that sea ice melt might not increase water levels, but it does actually increase global warming, because ice actually reflects a lot of that radiant energy from the light that comes into the earth. When sea ice melts, then it's less white and more of it gets absorbed into the ocean. So it does have this contribution to overall global warming. Now, we also are concerned very much about the ice that's melting in the Arctic, and there's been a lot of research recently that actually suggests that this is happening much faster than we originally thought, perhaps twice as much faster. And we're seeing substantial reductions in ice from the Antarctic. That is quite concerning, and probably will is making a big difference in sea level rise in terms of much of that increase that we're seeing, the 3 millimeters per year, is actually coming from the Antarctic as well as other sources. So reasons to be concerned about that. And remember that this sea level rise, when they're talking about 3 millimeters, it maybe doesn't sound so concerning, but this contribution actually is substantial in terms of the way that it impacts different areas. And it impacts different parts of the globe actually differently. So there are island nations that are actually having to move. So the island of Kiribati is actually getting flooded regularly, such that it's pretty much likely to disappear in the coming years. And they have plans to evacuate. They bought land in Fiji so that they're evacuating the entire nation out to another location that's at a higher level. So sea level rise is a big issue that we'll talk about later. Now, coming back to this idea of extreme weather events, we are just seeing more of them, and I'll just talk about some examples. We're seeing, IPCC shows that there is, as we see this increase in temperature, that there's likely to be substantial differences. And here's the key that you can see in later slides, but purple being very severe extreme impacts, possible entire destruction, down to white being no major impact in that area. And what the IPCC is predicting is, depending on how much increase in temperature we see, really substantial impacts in terms of extreme weather at a global level and impacts on threatened systems. And if you look at that at a more micro level at different types of ecosystems like warm weather corals or Arctic regions, etc., we could expect to see fairly substantial impacts at those different levels of heat. So remember, when we're talking about water, water is really important for the way that energy is absorbed in the earth. So a lot of the energy that hits the earth gets absorbed by water. Water has a tremendous capacity to absorb energy. We're fortunate because that has produced a sort of what we call thermal inertia, where systems will gradually reach equilibrium, and in many ways the water is actually cooling down the earth more than we would actually expect it to be necessarily if that water wasn't there to act as a heat sink. But it can take a very long time for that energy to reach the bottom of the oceans. In fact, it can take perhaps thousands of years. So a very long time where we can expect to see that gradual heating to impact deep ocean. So most of that inertia that we're seeing is from that ocean. And because of that, a lot of the warming that we are producing, we're actually just not seeing yet. And even if we stopped our emissions cold right now, no more carbon emissions at all, we would still see increases in temperature of about 0.5 degrees, just given the energy that's already been put into the system. So remember, when we're talking about this increase in energy in the water, for every 1 degree Celsius of increase in temperature, air can hold about a 7% more water vapor. And this makes a substantial difference. So we have currently about 4% more water than we had in the air than we did about 30 years ago. Now that water means that overall the globe, there's likely to be more precipitation around the globe, but that's not necessarily going to be equally distributed. So there are going to be some parts of the globe that will actually become much drier with droughts just because of weather patterns, and other areas will be getting much more rain. So it really depends on the case. But more water in the atmosphere actually means more extreme weather and storms. So if you look at, for example, hurricanes, so warmer oceans means that hurricanes can intensify much faster because the warm water contributes to the water in the atmosphere, and that warm vapor can produce really strong downpours. It can also, as these storms accelerate, for example, off the Caribbean, it can create storm surges that cause sea level to rise and cause real substantial damage. And then we also talked about this disruption where sometimes this wavy or jet stream can hold weather patterns in the same place for a longer time than we would expect. So Hurricane Harvey is an example of this, where we had a storm come off of the Gulf of Mexico, where the water was hotter than normal. This contributed to the storm and made a very strong, very wet storm, where we saw in Houston that the amount of 5-day rain was what we call a 1 in 25,000 year event. So we wouldn't expect that to happen, that amount of water to drop in 25,000 years. So 1 in 25,000 years. And some other areas is 1 in 500,000 years. So give you an example of that, in Nederland, Texas, they received 5 feet of rain, which is the most amount of rain that has been recorded in a single storm rainfall in the United States. So really big storms, really substantial impacts that we'll talk about later. But in addition to this increase in water, increase in storms, the heat that is causing this, that has influenced this, can also pull moisture out of the water, of the ground, creating drier, hotter weather. So this extreme heat is very extreme. So we will be facing that in the United States, but around the globe, sometimes it's really remarkable. So we're seeing actual temperatures of, in the 120 degrees Fahrenheit range, up to 130. And then we're seeing, if we look at the actual heat index, this is an example here from Iran, from Bandar Mashahar, where they reached 165 degrees Fahrenheit. And you can only survive for a couple hours at that temperature. Just really, really extreme temperatures. And, this also leads to drought. So areas that are facing this temperature for very long periods of time. This is a picture of near Chennai in India, where they experienced a very long drought. And these are some people pulling water from the last remnants of a lake that used to exist outside of Chennai. And they faced very severe water shortages where they had to bring in water, and you had to pay for it, and poor people couldn't get it and rich people could. And municipal water stopped running, so hospitals had to buy water to actually provide healthcare services. It was really a serious disaster. And then we also see, as heat increases, on average, we see more fires. So we're seeing that right now in Australia, where we're seeing very, very serious fires that are causing amazing destruction. So one thing I also want to note here, and this is something that we'll think about more as we go forward, but it's to remember that climate systems are complicated. Even though we have these models, even though we have some understanding of how these systems works, we don't know everything about this, and there are systems that we don't entirely understand yet, and we don't understand how much of an impact they're going to have on these climate systems. And this is one of the things that concerns me, is that things might reach tipping points that we're just not even aware of. So when we think about feedback groups, an example of this might be, I actually think I gave this already, was the idea that as Earth gets hotter, Arctic sea ice melts, so the sea becomes darker, so it absorbs more energy, and the Earth gets hotter, and that will in turn melt more ice. So we have a feedback loop of increasing heat. And then there's other things that, some of which we didn't really expect or understand. So thawing of the tundra has released a lot of methane, right? The effect of heat stress on forests can impact them. Methane hydrates. Water can absorb a lot of methane in lower ocean, and that can actually, as temperature can increase the release of that methane, right? So there are a lot of different types of systems, very complex ecological systems, that we're increasingly understanding can influence this feedback cycle, which is a good reason to think about this carefully and critically, especially when we think about ways to mitigate or decrease the risks that we might face from this increase in temperature. And of course, I'm going to come back to this, but these types of extremes in terms of weather can have major impacts on health in a wide range of different domains that we can consider as we go forward. So thank you very much for listening. That's a very basic and introductory rundown of some of the different things that we know from the science around climate and climate change, and to give us some thoughts about some of the different dynamics that we consider as we think about strategies for addressing this, which in terms of mitigation and adaptation going forward. So thank you very much for listening, and take care, everyone.